on cross-equatorial flow and the Somali jet. So, quick background. At the start of the monsoon, we have this cross-equatorial flow setting up in which winds from the southern hemisphere move towards the northern hemisphere, and at around 10 degrees north, they become zonal, and this zonal jet is called as the Somali jet. And this jet persists throughout the monsoon season with some intra-seasonal variability. And also, this jet is important for the summer monsoon rainfall as it transports energy and moisture from southern hemisphere towards the northern hemisphere. So here I have taken a snapshot from today from Windy, which shows this very strong jet, Somali jet, as well as feature of the low close to Odisha is also captured. And yeah, so talking about some dominant balances within the jet. So jet shows a very interesting dynamics, and if you look at the different locations in the jet, so here the yellow line shows the cross-equatorial flow, whereas the green contour shows the Rossby number 1 line. And at the different locations of the jet, you can see there are different kind of balances being present. So when and then these balances can be characterized by a non-dimensional number called the local Rossby number. Local Rossby number is just the local rotation of the flow divided by the planetary rotation, and we see that when the Rossby number is very small, of the order of 0.01, you have a frictional balance, and when this local Rossby number becomes close to 1, we get into a situation where we start getting an advective balance. So, along with its balances, the jet also shows a very rapid intensification at the start of the monsoon. So, within just 2 weeks of the start of the monsoon, we go from almost zero kinetic energy to its maximum kinetic energy, which is shown here by the red curve. And this rapid intensification can again be explained by the non-linear advective balance, in which the generation of kinetic energy goes as the square of the pressure gradient. So even if the pressure gradient is linear, the generation of the kinetic energy is the square of that, and then that can already give you a rapid kind of intensification. So if you see this black curve goes much more linearly from March to June, whereas the orange curve or the red curve, so the orange curve is the kinetic energy generation, and this generation leads to the kinetic energy. Is it a frictional balance at Rossby number? At what level you are talking about? So this is in the boundary layer. So jet is mostly in the boundary layer, and we are talking about 19 hectopascal, where the jet shows its maximum strength. It is stronger and similar to this. So friction between the surface and this one. Yeah, surface and the wheel. Yeah, so friction here is not been calculated. Friction here is computed as the residual of the kinetic energy budget. So we don't have a parameterization of friction here. Yeah, so whatever is left, we term it as friction. And if you look at the vertical profile of this residual term, you can see that near the surface, it's the maximum. So we can, with some confidence, say that the residual term is indeed the frictional term. Yeah, so within 2 weeks, it goes from seasonal mean winter values to seasonal summer values, and this is the rapid intensification. And now connecting the Somali jet to the monsoon rainfall, I think Professor Arindam a couple of weeks ago had already shown that the monsoon rainfall is very closely tied to the moisture flux within the Indian domain, and this moisture flux is modulated by the jet. So in that seasonal mean time scale, there is a very strong relationship between the jet and the summer monsoon rainfall. But if you see, even on a daily time scale, so here this blue curve shows the kinetic energy of the jet, and day zero corresponds to some criteria with which we say the onset on the jet has occurred. So we see the jet kinetic energy goes to around 150 meter square per second square, and then it stabilizes. And the red curve, which shows the central India rainfall, picks up slightly later. So this could be because the jet has strengthened and more moisture is being imported, and then you start seeing more rainfall in the central India region. Now I'll come to this recent study where they show that the cross equatorial dry intrusion can actually enhance rainfall. So this study came out this year in NPJ. And yeah, so let's just first look at the definition of dry intrusion. And here the dry, so in general, the dry intrusion is defined as the slant-wise descent of dry parcels from the upper troposphere to lower troposphere, along with so since it is slant-wise, it goes downward in the vertical levels, as well as it goes from the extratropics towards the tropics. And in this study, they have specifically used Lagrangian tracking for identifying these dry intrusion. So they will track the positions of all the particles as they move from upper troposphere, where they have very low moisture, and go towards lower troposphere. Along with moving downward, they will pick up some moisture. And the way they have done it is for each 3 hour time during the monsoon months for last 40 years, these dry intrusion trajectories are identified as the air parcels which descends from a level which is above 600 hectopascal, and within the 48 hours of their movement, they should go they should transverse at least 400 hectopascal downwards. So doing that, you can have these three categories of DIs. But the first one is the tropical DIs. So everything from the extratropics which comes inside the tropics, and tropics are from 15 south to 15 north, are called as the tropical DIs. And out of these tropical DIs, the ones that crosses the equator are the cross-equatorial dry intrusions. And finally, out of all these cross-equatorial dry intrusions, the ones which come up towards the Arabian Sea are called as the Arabian Sea dry intrusions. And in this study, they have only focused on the Arabian Sea dry intrusions. And yeah, so this is the frequency of dry intrusion during monsoon. So at the start, we see that a lot of these dry intrusions are present at 35, 40 south, which is because that's how they have defined it. And then after 120 hours, most of them have moved towards the tropics, and some of them have actually encroached into this Arabian Sea region. So if we look at the statistics, I think, yeah, 15% of the total, so 15% of these DIs can be considered as tropical DIs, and out of these 15%, 0.81% are cross-equatorial DIs, and 0.29 are the Arabian Sea DIs. So doing that, they have found out 137 Arabian Sea dry intrusion events, and this makes up for roughly around 3 to 4 dry intrusions per year. Yeah, now looking at the winds and the moisture following these dry intrusions. So the figure here shows the winds, which are black contours, the ocean evaporation, which are orange contours, and the moisture transport, which is the color shading. And TS represents the initiation of these dry intrusions over the southern extratropics, whereas TE represents the time when these dry intrusion initiation stops. So the time when DI ceases to initiate. So if we start at the start of the dry intrusion, we see this cyan color, which is somewhere close to 25 south. That's the location of DI at the start. And then if you see at that time, so these are wind anomalies. So the winds have started picking up close to that. And at the end of the initiation, so 90E, we see that there is a lot of ocean evaporation at this location. So this is the Central Indian Ocean, as well as there is a lot of transport. and we see that the dry intrusions are somewhere around 25 south now. And one day after these, we can see the dry intrusions have moved northward. Also, we see that the moisture transport has strengthened and the evaporation has also strengthened. Along with that, the wind anomalies have also picked up. And then when we see 5 days after the ceasing of initiation of de-ice, we see this region has now completely become still, the Central Indian Ocean, and all the action is going on in the Northern Arabian Sea, where you have very strong wind anomalies as well as strong moisture transport. So overall, enhancement of wind speed and moisture transport in the Arabian Sea favors about 10 to 20% more moisture transport towards the southern part of India. And now looking at the picture for total precipitable water and precipitation following de-ice. So again, all these symbols have the same significance, but now the magenta contour shows the total precipitable water, whereas the color shading shows the precipitation anomaly. So we can see that at the start, we see this dry, a negative anomaly of precipitation in the Indian region. But after 5 days of the ceasing of dry intrusions, we can see there is a strong negative, strong positive anomaly of precipitation in the Indian region as well. So this box they call as the target region, and all the results for precipitation in an average sense are shown for this box. But you can see that the rainfall has increased as well as the total precipitable water has increased. So the rainfall has increased by 17% following DI, and the total precipitable water has increased by 3%. And now looking at the differences between the climatological mean and the post DIs. So post DIs after the dry intrusion has stopped, we can see that this probability mean has shifted to the right, both for the precipitation as well as for total precipitable water. And so this is an important plot here, which shows that when there are no DI events, you see that there is a strong correlation between precipitable water and precipitation, which is obvious in a way. But the lag correlation between ocean evaporation and precipitation, as well as ocean evaporation and total precipitable water, is very small. So, by the way, the ocean evaporation is selected in the central Indian Ocean region. So, yeah, so this black box. So the evaporation values are taken from here, whereas the precipitation as well as the precipitable water values are taken from this black box. So in the situation where when there was a DI, we can see again there is a very strong correlation between the total precipitable water and precipitation at day 0, but there is a lag correlation between the ocean evaporation and precipitation, as well as the ocean evaporation and total precipitable water. So, ocean evaporation over the central Indian Ocean precedes total precipitable water by 2 to 3 days, and the moisture from the central Indian Ocean can take up to 2 to 3 days for to reach and precipitate over the Indian region. Now, they have also done a study of the Lagrangian time evolution along the DI. So in that, we will sit on top of a dry intrusion event, and as it glides down, we will track the properties of that dry intrusion event. And they have also done an Eulerian time evolution where you are looking at a box. So when you look at temperature, specific humidity, and ocean evaporation, you are looking at the central Indian Ocean box. Whereas when you are looking at total precipitable water or precipitation, you are looking at the Indian region. So starting from here, so that's how since they have defined their dry intrusion events in such a way that within 48 hours it has to glide from upper troposphere and at least move 400 hectopascal down. So we can see from day 0, there is this coming down of pressure. So from let's say 300 50 hectopascal, and around in 48 hours they come to around 850 hectopascal. And along with that, we start seeing that the specific humidity of these parcels starts increasing. This is because this dry parcel mixes up with the moist parcels from the lower troposphere, as well as it picks up a lot of moisture from the central Indian Ocean in the form of evaporation from the ocean. Yeah, so the evaporation also picks up, and the relative humidity also picks up since these parcels become more and more moist. And when we look at the Eulerian time evolution, we can see that in the central Indian Ocean, you have this again the temperature increasing, specific humidity increasing for some time, and evaporation suddenly increases. So this Ts by T is, so there is this sharp break between at day zero, because this, so day zero corresponds to the day when you have Ts, and again the next time step is when it ceases to uh, when the dry diffusion ceases. So basically any time after Te. So the important thing from here is that the total precipitable water starts increasing once the dry diffusion has stopped and all of the moisture has come towards the Indian region, as well as the precipitation also increases. And so this schematic summarizes the study in a nice way. So at 0th hour, dry diffusion starts from here, somewhere in the upper troposphere, from 300 to 500 hectopascal. And as they come in the central Indian Ocean, they have slanted downwards to 700 to 900 hectopascal, so in the lower troposphere. And when they are here, they mix up with the moist lower tropospheric air within this region, as well as takes moisture from the central Indian Ocean, becomes more moist. And also, since these parcels come from upper troposphere where their wind speeds are high, so this study speculates that there is a momentum transport of these high speed winds, and that also creates an increase in the wind speed. So the ocean evaporation goes up by 30%. Wind speed goes up by 10% to 30%, and then this causes an increase in precipitation of about 17%. But so this was a composite mean of all the dry intrusion events. But if we look at individual dry intrusion events, there is a lot of variability, and they have done a clustering analysis where they take all these 137 events and partition them into 4 different clusters, and we can see that there are these different clusters where actually the rainfall over the Indian region is decreasing instead of increasing. So basically, when we look at the composite mean, we are capturing the signal of this cluster and this cluster, since their magnitudes is much higher than these other 2 clusters. So if we look at the quantitative evolution, we can see for cluster 1, you have 44% increase in the land plus ocean region. So I think this whole box. And for cluster 2, there is a decrease. You can see that. So there is this dryness here. Whereas for cluster 3, most of the precipitation is confined towards in the Western Ghat region. And for cluster 4, again, you see this break kind of a situation. So I guess what they claim here is that dry intrusions can have both kinds of effect. They can also enhance rainfall. They can also reduce the rainfall. Yeah, so I'll switch gears now, and I'll just so I was looking at Somali jet, and I think when we talk about pirates, we always associate pirates with Somali pirates. So I was curious to see if there is some studies where they have done some study on Somali piracy and monsoon. So lo and behold, there is a study which is titled Somali piracy and monsoon, and the first line of the paper is nearly half of all the records recording maritime piracy worldwide in recent year has been attributed to Somali pirates. So that's why we know that when we talk about pirate, we always talk about Somali pirate. And what is the definition of piracy? So the International Maritime Bureau defines piracy as an act of boarding or attempting to board any ship with the apparent intent to commit theft or any other crime, and with the apparent intent or capability to use force and furtherance of that. So this study basically looks at what is the effect of monsoon winds on the Somali piracy. And this study is just been done for 2 years, and we see within these 2 years, these are all the reported piracy events. So the pluses are for 2008, 2011, and the circles are for year 2010 in the Arabian Sea or the Somali region, and we can see there are a lot of these piracy events for these 2 years. So this is like 287 events in just 2 years. And on the right, we have this our favorite Somali jet. Now, if we try to look at the wind speeds and the latitude of the attack, it is very clear that when the wind speeds are high, so during our monsoon season, summer monsoon season, there is no circles here, which means that there are no attacks. And when the speeds are low, we can see this clustering of all the pirate attacks. And this wind speed data was taken from a single station at island, whereas this is a box averaged. And even in this, we can see that the wind speed is similar. So we can again see that during the summer monsoon, the pirates are not attacking the ships. And this study also asked if there is a threshold after which the pirates stop attacking. And turns out, at least in the data, there is this threshold of 9 meters per second. So here, this histogram shows the wind speed and the number of attacks. And you can see, and these dark shadings are successful attacks, whereas these are all the attacks, the normal plots. And so there are these some brave pirates which, even after very high wind speeds, try to attack the ships, but they were unsuccessful. So, in summary, after the wind speed of 9 meters per second, there are no successful attacks in these 2 years of the data.
But then why not move to the lakes?
Why is it not skewed to the left? That is a good question. Yeah. I guess pirates can't differentiate between 2 meters per second and 5 meters per second. Yeah, but that's a very good question. And anyway, so I was looking this up and I actually found a Wired article where they say climate studies show Somali pirates take summer vacations too. And yeah, and they say that this is for different reason, and we all know what the different reason is. It's the strong Somali jet. So, in summary, in this study, in today's talk, we have seen that cross-equatorial flow during summer exhibits different balances at different locations, as well as a rapid intensification, which can be explained by the non-linear advective boundary layer. Also, dry intrusion events from southern extratropics during the monsoon can lead to enhanced rainfall, but that's not always the case. There are events, even dry intrusion events, in which the precipitation actually goes down. And also, Somali pirates take vacation too, but these vacations are forced. Yeah, I think with that I'll end.
Strong winds from south to north. Each direction of the element transfer. Yeah. Ocean.
Yeah. Yeah, if
Is it a function of that? Because they can't cross that long. They cannot come in the ocean.
There will be a baseline of cutting. There will be a kind of cutting at the Somali coast.
Yeah, that is there.
Yeah, I mean,
is there any problem with the shear?
no, at least this study does not talk about any of that. So I guess their goal is just to say in each season you have more pirate attacks. Since the wind speeds are higher, I guess, and these pirates actually do like attack on very small ships. So probably these turbulent weather events around that location will not be good for their ships. So that's why they don't attack. Yeah.
Another thing is there's a thing out there. Captain 3, based on Somali pirates. So actually, when there is a winds are very strong of waves,
Yeah.
their ships are very, they waves are shaking.
Yeah. That could be the case because most of these attacks have been done from small ships. If the ships get bigger, maybe they will be able to attack during summer subs.
When the increasing ocean average will also increase, and transfer increase. So ocean mixing will also increase. Right. So SST would change. So I wanted to ask, what is the time scale of change of SST? Is number one. And number two is how will the atmosphere react to the SST change within that particular time?
The first part of the word, right? Sorry, was it the first part of the
Yes, this was
dry and
Yeah, I mean, I have no idea. So I don't know what the time scale will be. And but if you, I guess, look at it in a way where the particles, you are just tracking the particles, that does not matter yet. Maybe these four different flavors or the four different clusters is because sometimes the ocean evaporation dominates, and I mean there is not a lot of moisture transport from the ocean towards the lower troposphere, and that's why only the dry air goes with the jet. And since the dry air goes, you will have like less than normal precipitation, and there could be other factors also. So I'm not very sure.
Can you comment a little bit about the time scale of this event?
Time scale of which event?
The moisture not affecting and the dry is still going.
I can't, but these guys have done, I think, a separate study where they track all the particles in the globe for all the seasons and try to do try to see how the ocean evaporation is evolving and how the specific humidity of the parcel is evolving. So one has to look at that, I think.
thank you.
I'll put your slides.
Rajat, I have a question. Can I ask? Vishal
Yeah,
here,
sure.
online.
Yeah, sure. Yeah.
So Rajat, actually, I have a question about dry intrusions. So as you mentioned here, actually, this is the perfect slide. So green is where the parcel starts and slowly descends, and as it reaches the Arabian Sea, it's already dry as compared to the environment, and that's advected through the Somali jet over India. Is that the correct understanding, or something else is going on?
Can you repeat that?
So the parcel starts where it's green in the left figure, and by the time it descends, it brings whatever, I mean, adiabatic warming and dry. I mean, it brings in the dry air. So the air retains its identity by the time it reaches Arabian Sea. Is that the correct understanding in the study?
No. So if you see the orange contour here, so it has not reached the Arabian Sea yet, but it is already somewhere around 700. So in the lower troposphere or in the boundary layer. So it is already moistened up.
Yes. So exactly my thinking was this is an anomalous dry, I mean, intrusion, right? So usually you have a lot of moist air through Somali jet that would come over India. And if anomalously lesser moisture is transported, then it is called dry intrusion. Is that the definition? Or the air is really actually coming down from 200, whatever, 300 hectopascal and mixing with the boundary air in the boundary layer and causing the lowering of humidity, which is transported later on.
I think that's the latter. So the definition is any air which comes from the upper troposphere, and as it slants downwards and northwards, from the south extratropics. It takes up moisture both from the lower troposphere as well as, in this case, from the central Indian Ocean. So here when they define DIs, they do not really look at the moisture initially. They just look at the parcels at the top and just keep tracking them. But if you see other studies related to dry intrusion, they define dry intrusion based on the specific humidity of the parcel at the start. So they are already dry.
Right. Okay, and the second kind of related thing is, this is not really the Lagrangian parcel tracking, right, per se. It is probably Eulerian data looked at from Lagrangian lens. Am I correct?
Yes, yeah. Because that's the best you can do, right? Because you have to have a velocity field and then you integrate it over time to get position vectors. And that
No, but then
velocity field has to come from reanalysis.
Right. Then all the processes which cause mixing on fast time scales could be, I mean, well, we'll have to worry about it. But it's a very nice study. Yeah, thanks a lot for telling us about it. I guess Deepika, the first author in this, is also in the audience, I guess. So congratulations.
Oh.
Thank you.
Yeah. Thanks, Vishal.